Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Rola Dbouk with us today. Hello, Rola.
Hello, Frank. Francis, how are you?
Oh, Francis. Ooh, my mother calls me Francis, but you.
Hi, Frank.
Francis is good. It's my real name, but Frank's okay. Rola, where are you located at?
I'm at MIT, so Cambridge, Massachusetts.
Ooh, Boston. So do we have snow on the ground yet in Boston?
Not yet, no.
Oh, it is November 9th, 2023 as we record this, hence the question. But not yet. Okay, let's see. So I'm in Phoenix, and we are definitely coming into our fall mode, I will say. So it still gets pretty warm in the afternoons, but the mornings are cool. So we're doing good. Very cool. And what is your position there at MIT, Bola?
So I'm currently a fourth-year PhD student
Oh,
in the planetary science program.
cool. And when do you anticipate graduating?
In about a year and a half.
Okay. Well, I very much look forward to seeing Dr. Rola.
Thank you.
Very cool. And Rola, what do you like to do for research?
So I currently work on the tidal evolution of planetary satellites.
Okay.
That is, we do a lot of n-body simulations, and yeah, we can study also spin-orbit coupling because of that tidal evolution.
Yeah, cool. Very nice. That is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. Go grab a copy for free. The origin of Jupiter's obliquity, and Rola, take us away.
Okay, so as the title says, this paper is about the origin of Jupiter's obliquity. So Jupiter's obliquity is currently about 3 degrees, which is, so it's kind of small, but we will still require some explanation for that. So like the first sentence in the paper, if the planets grew smoothly and continuously by accreting small bodies and gas from an isolated flat disk, then their obliquities should be 0. So that's again why we need an explanation for this small obliquity. The motivation for this work actually was related to the idea of the like unexpected rapid migration of satellites, which was first measured, like here we mentioned those measurements for Saturn. Titan, the largest moon of Saturn, was found to be very fast, had a very fast rapid migration, and that was unexpected. So the scientists thought that with Titan moving away from Saturn, it could actually be affecting the spin precession of Saturn, which is basically, yeah, like equation 1 here shows the precession rate alpha for the spin axis of the planet. Okay. And there's the Q term, Q and L, both these involve parameters related to the satellites, which is shown in equation 2. And you have the A, or A sub J, which is the semi-major axis of those satellites. Yeah. So as the satellites move away from the planet, A increases, and then Q increases, and then alpha in turn increases. So you have this alpha, which is the spin precession rate, increasing. And if this frequency crosses some of the frequencies of the modes of the solar system, then you would have a resonance.
Yay. Yeah. Gotcha. Very cool.
So for Saturn, it's believed that this the spin precession resonance with one of the modes of Neptune's orbit caused the increase in Saturn's obliquity to the present day value. Okay. And for Jupiter, what we're doing here is kind of similar, but has some differences, of course. So first of all, the moment of inertia of Jupiter was not very well constrained in the past. And scientists thought that the resonance that could have caused Jupiter's obliquity was actually a resonance with Uranus.
Ooh, okay.
Yeah, but with the very new determination of the moment of inertia of Jupiter by Militzer and Hubbard in 2023, which is very recent, we were able to rule out that scenario with Uranus. Okay. So yeah, that was mentioned here. That's the value 0.26393. That's a very accurate number, just above.
Yeah, right here. I'm just getting this one to fit. There we go.
And so with this new determination, we found out that the resonance with Uranus was actually something that could be encountered in the future, but not in the past. So it could not be the reason for Jupiter's obliquity. Okay. We needed a different resonance. So I guess we can go to table 1, where we show the frequencies of some of the like inclination precession motions in Jupiter's orbit. And so the G7 is that mode that is related to Uranus that scientists attributed to cause Jupiter's obliquity.
Okay.
But in fact, we computed alpha, the precession constant for Jupiter's spin axis, and we find its value to be, it's just slightly below the table. It's there, it's 5.306 times 10 to the 5, the period. And this period is inversely proportional to alpha, of course, because it's the frequency.
Yeah.
And if we place this period like in a certain place in that table, it would fall between the third and the fourth rows. So that would mean kind of there, and in terms of periods, yes. So since alpha is an increasing function of time, then the period of the precession is a decreasing function of time. So G7 falling just after the period that we just talked about means that it's going to be encountered in the future, not in the past, and that the most recent resonance was this minus F5 plus F6 plus G6 mode. And this is the resonance that we think was actually the reason for Jupiter's obliquity. So to discuss like how much of an excitation this resonance can cause to Jupiter's obliquity, we could look at equation 4. So in equation 4, there is this expression from the literature that gives the excitation or the increase in the obliquity theta for a resonance that was passed adiabatically in the direction for which capture is not allowed. So this is the case if like alpha was a decreasing function of time, which is not what we have. We have an increasing function of time. However, it would still give us like a good order, like approximate value of what's going to happen. And using this equation, it actually depends on beta, which is the strength of the resonance. Those are the like all the beta values are found in table 1 for some of the resonances. And using the one that we believe is actually the one causing Jupiter's obliquity, we find that theta 0 is going to be 4.6 degrees. So this gives an order of magnitude, which is close to the 3-degree obliquity of Jupiter, so that we're going in the right way. And then
a question here, beta is I over 2, I being the moment of inertia.
No, here I is the inclination of the orbit. We call the moment of inertia lambda because it's a normalized moment of inertia. We're calling it lambda.
Thank you. I'm good.
So then we developed a resonance model to actually investigate this resonance passage. This is the Hamiltonian that we use. You can see alpha over there, the precession rate that we talked about, and lambda, the moment of inertia. So the Hamiltonian basically depends mostly on these two parameters, and also on the evolution of the orbit of Jupiter, of course, which is evolved in the model based on these equations 3 on the left. So we include this I, the inclination, in terms of a summation over the beta, gamma, and delta shown in the table. So I'm
with you.
And then we can go to, there's also equation 6, I guess, that has, so this is another equation for theta again, for the excitation, but this is different than equation 4 that we talked about. So here, this is a non-adiabatic obliquity in the limit of large alpha dot. So it is in the right direction. So this one is used when alpha is increasing, like the case that we have. But this is a non-adiabatic passage of the resonance. And the reason this is important is because the current obliquity of Jupiter is not very high. And we found using, n-body simulations and the new determination of the moment of inertia that the obliquity of Jupiter currently is oscillating. It's not in a resonance with any other mode. So if we're going to explain the obliquity of Jupiter using some resonance, it must be a resonance that was crossed but not captured. Because if the resonance is captured, you would expect that it's currently in the resonance and the obliquity keeps increasing as we go further in the future. But we're not in the resonance, so we thought that it could be a non-adiabatic passage. And non-adiabatic means that it happens that like crossing the resonance happens so fast, like this, the change in the precession rate of Jupiter's spin axis is much faster than like going one cycle around the resonance, so it cannot be captured in it. And this equation provides like an upper limit, like just a limit where for large alpha dot, so it's not exact again, but it also can give us a good approximate value. So if we go to first figure,
figure 1. Here we go.
Figure 1,
Please.
So here we have theta, the obliquity, versus alpha dot, the rate of change of the spin precession. And the black horizontal line was the 4.6 degrees that I mentioned in equation 4. So that's the adiabatic passage, but in the non-capture direction.
Yes.
And then the purple curve is the it's the non-adiabatic passage, but in the capture direction.
Yes.
So the black is adiabatic and the purple is non-adiabatic. And the blue points are those that we find using the resonance model that we developed. So in this case, we run the model for a certain fixed alpha dot, which we give, which means that alpha is basically increasing linearly with time because we're fixing alpha dot as a number.
Yes.
Yes. And for each simulation, for each different alpha dot, we run the model and then we plot one point here showing what is the final obliquity theta that we get after the resonance crossing.
Got it. I'm with you.
Okay. And we find that it's actually kind of in between the black curve and the red and the purple curves. That's a good the equations were kind of good approximations.
Right.
And the red horizontal curve is the present obliquity of Jupiter.
Okay.
And that's what we're trying to explain. So basically the intersection of the blue dots with the red curve is exactly what we need. It's going to provide us the value of alpha dot, that is about 4.5 or 6 times 10 to the minus 16 radians per year square.
Okay.
So after knowing that value, we can then run the resonance model again, but with a more kind of complicated equations. We don't put alpha dot as a constant and evolve alpha linearly with time, but we actually provide migration rates for the satellites and let the system evolve based on the evolution of the satellites.
Okay, good.
Such that it would cross the resonance with this alpha dot that we just found here. So it would have the exact precession rate that we need and rate of change of precession rate at the resonance crossing.
Cool.
So so to do that, we then look, there are some equations for resonance locking, which is those like 7 and 8, for example, because we run the model based on the idea that the satellites are evolving with this resonance locking expressions. There are measurements actually for Ganymede and for Europa of how much they're evolving, but there are not measured values yet for Callisto. Okay. But we're going to assume that Callisto could also be migrating, and that's what also scientists in previous works have done. So we use these equations 7 and 8, put them in the resonance model, and we can, I guess, the table next, table 2, can show us the values that we were using.
I'm with you. Okay, let's go to the next table. Migration for Ganymede and Callisto. Yeah, so in row 2 of this table, yes, we have we assumed like a tidal migration timescale of 9.6 for Ganymede. Okay. And using the resonance model, we were able to find what's the tidal migration timescale for Callisto, which is about 130 billion years here. And these values can also be translated into A dot for for Ganymede and Callisto. These are the migration rates. Cool. And this row basically is dependent on the measurement done by Laney, the 9.6 billion years. Okay. And also another case, which can also reproduce the obliquity of Jupiter, the third row, we use 20 for the tidal timescale of Ganymede, and that is assumed by Fuller in the resonance model paper. Yeah. And we can also get like what is T-tide for Callisto and the migration rates. We also did hypothetical cases like the first row and the fourth row, where we put infinite tidal timescale for either Callisto or Ganymede, and that means that satellite is not migrating; it has an infinite timescale, but the other one is only migrating. Gotcha. So this provides an upper limit on the migration of the other satellite. In the first row, you have infinite tidal timescale for Callisto, which means 0 A dot. Yes. But for Ganymede, that means 38.4 billion years or 12.8 centimeters per year for Ganymede. Cool. And the last row is an infinite tidal timescale for Ganymede, which says that tidal timescale for Callisto, which means it's 0 for Ganymede A dot, and then 12 billion years for tidal migration of Callisto, which is 15.7 centimeters per year for the migration of Callisto. And that's, I think, an important number to note, because there's no measurement of that number yet, and this is providing an upper limit. So basically that's
a good thing to know and to compare for future measurements.
Absolutely.
And so finally, all of those 4 cases can produce something like figure 2 here, but specifically we use the second row in this table to do this figure.
Okay.
So that's like using the resonance model, starting with the 0 obliquity, and then letting the model evolve into 4.5 billion years. And around at 3.3 billion years, we crossed that resonance that we talked about. And you can see how the obliquity actually jumped up, this excitation.
Nice.
It reaches a value where it currently oscillates about the current mean obliquity of Jupiter. So that's basically the result of the paper. Yeah.
It's a money shot here. Very cool.
Yeah.
Okay. And the time scale. Okay. Gotcha. Nice. Very cool.
Yeah.
Awesome. Good. And we round out. And so we're looking for this minus F5 plus F6. Okay.
Plus G6 resonance. And that is the reason for this obliquity jump. And this explains the obliquity of Jupiter and also provides upper limits on the migration of the satellites.
Right. Cool. There's also 2 appendices here. There's one about the one I asked about earlier, moment of inertia, and the mean obliquity of Jupiter. So you may want to check those out too. Those are pretty good.
Yeah. Like the first appendix gives how we can also compute the moment of inertia using a CLC method that Jack, my advisor, developed. And this one uses like updated values from the Juno measurement, so it provides a very accurate number. It is in very good agreement with the Militzer and Hubbard number that we talked about in the beginning of the paper.
Cool.
And also Appendix B is where we did the mean obliquity of evolution of Jupiter. So we did n-body simulations, took into account that newly determined moment of inertia. We found that the obliquity is not in resonance and it's oscillating about 3.2. This is with respect to the invariable plane.
Yes. Okay. Okay. Yeah, I was going to ask this question earlier when we were looking at figure 2, but it's right. So
yeah, all the thetas are
kind of gives you the time scales on variations. Very cool.
Yeah.
Very nice. Beautiful paper. Beautiful. Rola, I want to thank you so much for walking us through this very awesome PSJ article. Very nice.
Thank you.
And you kind of touched on it a little bit there. And so let me push on that a little bit. Where do you think we go with this work over, let's say, the next 2 to 5 years? Is there additional observations that can be done? Is there additional theoretical work on the model? Can this be applied to, let's say, Saturn instead of Jupiter? And dare I say anything about exoplanets? So just sort of next steps, where do you think we go from here, given the published article? Okay,
so for applications, it could be applied to systems that have, I think, more or less lower obliquities. For Saturn, the obliquity is currently 26.7. So that requires like capture in the resonance to get that, I think. And in terms of observations, so it's very exciting if we get some observations, especially for Callisto's migration, because it's not has no measurements yet. And we could have some Earth-based observations, but I think the exciting thing is the JUICE mission, which was recently launched, and it would reach Jupiter in 2031. So that's a long wait, but it could actually have some measurements that are very relevant here.
Yeah, very cool. Nice.
Yeah.
Super. Well, I really look forward to seeing some explanation of Jupiter's obliquity, and this will be pretty cool as it moves forward. So very nice. Cool.
Thank you.
Well, thank you so much once again.
Thank you for having me.
Sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.